Hey, this is Andrew. I'm doing a real short video to show how to do CAM in Fusion 360. So if you look over here, this is our main Fusion 360 window. This is what you get when you open up the application. You should be logged into your own personal account. It should be an educational account. Before you start the CAM, you're going to want to make sure that you have the manufacturing extension turned on. So if you go over here to the top right, go to extensions. This little screen will pop up, and you can see I already have it here. It says active, but you can click on it, and somewhere around here, if you don't have it active, it'll be able to enable. It's a free thing you get for 30 days. You just re-enable it every 30 days that you need it. So make sure you do that first, get that downloaded, because that's how you get the actual CAM tools to use. Once you get that, we'll start off with the actual CAM. So I have a folder right here. This says CAM training. That's something I created with some part documents that I've already imported. If you are doing a new CAM project, so I consider a CAM project to be like a sheet of material or a new part if you're just doing a single part. But usually try and do CAM for like a router, you do a whole sheet of material. So you create a new project for that. So I already created it. It's called CAM training. So I'm going to double click it. And inside here, there are two parts. These are parts I already pre-installed. If you want to add parts, you're going to want to download the step file from Onshape and then go to upload. You'll upload them here, say upload. It'll take a couple minutes, but they'll appear over on this sidebar. Something to note, if you're doing router parts, you're going to be having a single thickness of part, so a single thickness of material. So you want to make sure any parts that are in this project folder are the same thickness. So for this example, both of these parts are 1/8 of an inch thick, which is 0.125. You just want to make sure that you're not mixing and matching different thicknesses. In theory, that's possible from a CAM perspective, but because you only have one thickness available of material on the router at a time, you want to make sure you're only cutting all the 1/8 inch parts with all the 1/8 inch parts, all the 3/16 with the 3/16, and so on and so on. So this is what we have as our setup. So when we dive into it, the first step that we're actually going to do is just take our parts, and we're going to drag them in. So click and drag, and it's just going to automatically generate somewhere. Say, okay, it doesn't really matter where. You can see the part is there. Now, some of these parts we're going to have multiple of. However, we're only going to drag in one of each unique part. So we'll make it multiple parts later on. So we have these two plates. This one's a little bracket here, which was I used on the 2024 1351 robot as a gusset. And this was also used on the same robot, I think, on the intake. So these are both nominally 1/8 inch parts. This piece right here, I'm highlighting in blue, I'm going to make multiple of, but I'm only going to do that later on. For now, I'm just going to drag one of each. So because I have two unique parts here, I should have two unique parts here. So that's your first step. Just drag them all out to the field. The second step is we're going to arrange them into the sheet. And the way we're going to do that is actually a tool that does it for you. So if you go to the Modify section up here at the top, you go down to Arrange right here. It says quickly arrange items on a plane or sketch for manufacturing. Makes it great. Super simple. So the first step, you see this little arrange window pops up. You have objects and envelopes. I like to jump straight to envelopes first. We'll go back to objects in a second. The first thing we want to say is we want to make our envelopes arranged on a plane, not a sketch or a face. So we're going to say a plane. And then somewhere here, when we select that, our little plane triangles will appear. I want to select what I call the XY plane. So that's going to be this one right here with green and red. So green and red is the default in Fusion. Green, I believe, is Y and red is X. So we want to select that one. From here, we're going to set the size of our envelope. Now, there's length and width, X offset and Y offset. Ignore the offsets. We're not going to be using those at all. Those should remain as 0. So length and width will be whatever the size of your material is. So I usually use material at something close to like 22 by 28. It could be 24 by 28. It really doesn't matter. Make sure that you have accurately measured the material that you're going to use. Something that I've always gotten a little confused about, it gets me every time. Length and width are not what I would describe as length and width. They're actually a little flipped. So if I wanted something that's 22 inches tall or 22 inches wide and 28 inches tall, I would think to say 28 is the length and 22 is the width. But if you look at this, it's hard to tell. That looks more like a rectangle that's wider than it is long. Now that's just their verbiage, that's just their orientation. So this will be 28 by 22. I want it the other orientation. Just for me, it just makes my head easier. You can rearrange it any way you'd like. It doesn't matter. I just flip length and width. So 22 by 28. Oop, not 8, 28. Boom, all right. It makes something a little bit nicer, at least for my brain. You can do whatever you'd like for it. If we scroll down to the next section, we don't need to limit envelopes. We don't need, we can allow partial arrange, that's fine. Nothing here we need to touch, no grain direction. Spacing, here's where some interesting stuff is. So frame width, if you hover over that, it gives you a little definition. It specifies the width of an empty border within the arrangement area. So the way my typical work style is, and I'm sure yours will be as well, I tend to mount my sheet of material on the router using a bunch of wood screws to some stacked sheets of MDF. Those usually go on the outside. So I want to make sure that I'm not putting parts, or that Fusion isn't putting parts that intersect with those holes. So we make that frame width 0.75 inches, about 3/4 of an inch. This basically says that the outside of the envelope is untouchable for 3/4 of an inch. Now object spacing, this is how close your objects can be. At the end of the day, the theoretical minimum is going to be your end mill diameter. If I'm using a 4mm diameter end mill, then the smallest I can have is a 4mm spacing between parts. Any smaller, and then my end mill is going to risk running into and cutting off pieces of those parts, which is obviously not something we want. I typically go to about 1/4 inch. You can go bigger, smaller. 1/4 inch is the default size. I think it works just fine. There's a little bit of merit to exploring something like 3/16. That's just a little bit bigger, but I would not complicate it. Envelope spacing is if you're planning on having multiple envelopes, so that would be multiple machining plates right here. In theory, you can do that. It just doesn't really make a whole lot of difference for this. You can just leave this as whatever the default is. So we're going to go back over to objects. And this is where we're going to select our components. So we'll zoom in. I'll select this one, and I'll select this one. You can see them appear, and see there's our mock-up of our aluminum sheet. You can see the blue outside is that 3/4 inch border that we defined earlier. You can see the parts are fully within the inside of it. And then this is listed as 28 by 22. Now, where we go over to quantity over here, we have the parts listed out. We can do a couple things. You can flip the orientation. You can set a priority, although we don't really care about that. Most everything is going to be the exact same because we're doing it all manually. Quantity here is listed as global, which simply means whatever this number is. It's a global quantity. So if let's say I put all the parts in here. Let's say I put a full robot's worth of 1/8 inch parts in here, and I say, never mind, I'm making 2 robots. I can just double global, and that'll just make 2 of everything. But for the most part, I like to keep it pretty straightforward and keep it simple. I'll just manually set all these. So if I go to this first part, this arm gusset, let's say I want 4 of them. Go 4, boom. And you can see 4 has been arranged. And for this 1351, I'm going to go 2, boom. Now you can see it's set to a given size within this area that I set, within this 22 by 28. If for some reason I want to make it smaller, I can go back in and say, hey, 28 inches is a little too long for what I want. Maybe I want to fit it within like 18 inches, right? Try that. And you can see it rearranges. So if the sheet of material I have is not exactly the right size, or maybe I'm just trying to compress, maybe I have a 22 by 28 inch sheet of paper, or a paper of material, but I say, hey, I can condense all these parts instead of taking up all that space. I'll do something like that, and it works great. For the purpose of this, I'm going to put this back to 28. It's not the ideal packaging, but it works well. I just want to put this back here just so we can show for the tutorial. So we have the envelope set correctly. If we go to the objects, those are set correctly. So we say okay, and that's our arrangement. Now if you notice, our arrangement's over here, and we have a new thing over and on the top left that says arrangements. But these are still our original parts that we dragged in. They're right here, right here. Now, for all intents and purposes, their job is done, and all they do now is get in the way. So I like to hide them. So you click the little eyeball, hide, make them go away. Don't care about them. So now we're completely done with the arrangement. If you see, we're in this little tab called the Design tab. We're done with everything in the Design tab. So we have our arrangement created. The next step is to actually do the CAM. So if you click on the Design tab, go on down to Manufacturer. We're going to go to the Manufacturing tab. It gives a whole bunch of different tools. So the first thing we're going to do is we're going to do our stock setup. So we go over to the setup area. You'll see a setup, and you'll see an NC program. We want setup. We don't want NC. If we click on that, you get this weird yellow volume surrounding our parts. And that's going to be an attempt at defining the stock. And we're going to do that quite easily, actually. This right now is an undefined stock. It doesn't know what size our components are, and it's just sort of guessing. So the first thing we're going to do, we have this little stock setup over here. We're going to go to the model section. Under the model selection, we're going to say select. And once you click on select, we need to select what our model is. Well, our model itself is going to be that arrangement we created. So if we go up to the top left, you can see models up there. And just click the arrow and go down. Whatever this file is, it's unsaved. We'll just go down again. And inside here, that's the old thing that we saw on the design page. We're going to go to arrangements. We'll find this arrange 1, 1, whatever the number may be. We're going to select this arrangement, and boom. It's going to automatically create a stock based off of that arrangement and that material thickness. So that's going to be helpful. So we want to say orientation is going to be not based off model orientation, which is the default. We're going to say X and Y axes. So we select that. And we need to select what the X and Y axes are. So right now it wants me to select the X axis. I'm going to zoom in onto this red line here. Make sure I'm holding the line, not hovering over the line, not the plane. Select that line as the X. Now it wants me to do the Y. So I'll scoot over this little green line over here. That's my Y axis. Now it looks like I did nothing, right? It looks like well, that's kind of how it already was, Andrew, and you didn't really change anything. And that's true. In this situation, I was lucky. I didn't change anything, so it happened to go to the correct corner. It doesn't always do that, and sometimes the origin sets itself in the middle, and you don't know what to do with that, or it thinks you're in the wrong orientation because you selected a different plane. So this is just a good way to ensure that things are done correctly. It's an extra step that takes a couple seconds to make sure everything's good. So next we want to select the origin. We want a stock box point, which is exactly what we have. So right now the origin is this dot right here in the center. To the tool orientation origin. What we care about specifically is the component origin, which is this dot right here. The stock origin, I should say. In order to select that, we select a stock point or a box point. When I click this button, this highlights blue. You're going to see all these little dots highlighted. And this is going to be all the different spots, the pre-generated spots we can do. Now I personally like to set my default as the bottom left-hand corner, but the top of the material. So if I say this section is the front of my machines, the front of my router, that section is the back, then the front is going to be this half right here. Or I say the bottom left, this would be the quote-unquote bottom left is, this is the left-hand side. That gives us one of three. We can either do this point at the bottom, this point in the middle, or this point in the top. Well, we can't super easily measure the point on the bottom. I can't think of any good way that's reasonable to measure the point in the middle, so I like to use the point in the top. So I'll select that. You can see this origin sort of pops up to the top. And this says we're going to say our Z0 is on top of the material. Our Z-axis 0 position is on top of the material. So that way when we're zeroing the router, or whatever machine you may do this on, I'm designing for a router mill kind of system. You just need to zero off the top of the plate and you'll be good. So we have that set up. We've already done our model. We don't need to worry about a fixture. We don't need to say what the machine is. This is as if you want to do like a preset fancy Haas machine. You can. There's merit to doing that. If you're using like a generic CNC router, like an Omeo, don't set a machine. It doesn't really matter. All we care about is the operation is milling. Now go over to our stock. Now, depending on what your presets are, this probably won't be already set up for you. We want our stock to be a relative side box. And we want our stock offset to be add stock to all sides. Boom. And what that means is we're going to take, so if we have no offset, it'll look something like this. If you notice, this doesn't include that 3/4 of an inch. This is just including the components. But we want to include that extra 3/4 of an inch. So we say we want to add stock to all sides. And then we're going to set our negative X, our positive X, our negative Y, and our positive Y offsets all as 3/4 of an inch. And then Z should always be 0, because we're not actually offsetting off the Z. We're just offsetting our X and Ys. So we have that. We don't need to worry about the post-process tab. We'll care about this later. We say OK. And that is our setup. It takes a second to load, and here we go. So we can go over to our setup. We can see over on the left-hand side, if I collapse the models tab, we have our setups tab, and we have a setup in here. This setup is our machining setup, and that's what's going to hold all of our tool operations and information. So now we're actually ready to start doing the CAM. I know after all this, finally get to do real CAM. So the first step we're going to do is figure out what our machining operation is going to do. Now, there's a lot of machining operations to choose from, and I'm not going to go over all of them in this video. In this video, I'm going to go over the 4 operations, 3 unique and 4 total, that we will be doing. I use these for pretty much every single plate robot part in the world that I've ever needed to make. It's very simple. It does everything you need, and it's pretty fast. So the first step we're going to do is we're going to do a boring operation. Not boring because it's not fun. It's called a bore because that's the machining term. It just means using a spiral to cut out a hole. So we have a circular end mill. We're going to drill all these holes. I don't want to say drill because we're not using a drill bit, but we're going to machine out all these little holes, all the circles, not the 1351. That comes later, but all the holes. So that'll be the first step. The second step will be something that we call an adaptive clear. It's a high-speed machining path that you use for pockets and for cutouts, something like this. So if you look at the 3 or the 5 or the 1s, those would be an adaptive clear to remove material. It's a fancy machining term. Once we're done with removing all that material, we're going to want to come back in to the same pocket, to the 1, to the 3, the 5, and the 1. We want to come back in and smoothen out the edges because our adaptive clear is a little messy. It's really good at removing material, but doesn't make a very clean finish. So we're going to come back in with what's called a 2D contour, and that's just going to draw out the shapes and smoothen out the edges. We'll go and do that. And then at the very end, we're going to do another 2D contour. So our 4th operation will be a second 2D contour. In that 2D contour, we'll cut out all the parts, and it will be done. It's very straightforward. So it's a very short overview. Let's get started with it. If we go to the 2D machining operations tab, you'll find bore in here. So the first step, you got to select a tool. Now, there's a chance that the machine you're on does or does not have a tool. If you go to the library, my library is empty because I just downloaded Fusion for this. So there's nothing in here, so I'll teach you how to create and insert a new tool. So I'm going to go to the library. I'm going to say a little plus mark right there. So we're going to add a new tool. So we want to use a flat end mill. Unless you're using something different, if you don't know what type of end mill you have, just assume it's a flat end mill. So in the description, I'm going to call it example 4mm end mill. And I don't care about the vendor or product ID or product link. So go over to the cutter tab. We're going to say it's a flat end mill unit. The unit I'm going to leave in inches because we're going to measure most of what we're using with this in inches. The only thing that's in metric is technically I like to use 4mm diameter end mills, and millimeter is metric. But don't worry, there's a solution for that. So we'll leave it in inches. Clockwise spindle rotation. Number of flutes. That's the number of little cutout shapes on it. A lot of what we use for the router are single flute end mills. So just one will work perfectly. We'll do that. Material, high-speed seal. It doesn't really matter. It's not going to affect any of the actual cam. So the diameter here, I'm going to put 4 millimeters. And it'll go 15748 or something. Make sure that this number is something you actually measure and confirm. I'm using 4 millimeters as the example, but you're going to want to measure to the diameter of your end mill, and you should have some sort of whiteboard or something that shows where your end mill diameter is for that machine at any given moment. And whatever it is, if yours is instead of 15748, if it's 15621, you just go 0.15621, right? Something like that. It's not always going to be precise, but I'm going to say 4 millimeters just to make it easy. Shaft diameter, it sets it equal to the tool diameter. That's fine. That works for us. Overall length, length below holder, shoulder length, flute length. For the router, we don't care about that. These defaults are fine. If you're using something on a CNC mill, then you care a little bit more, but that's not what this tutorial's for. The shaft, we don't care about the shaft. We just care about the cutter, and this is more if you care about the, if you're doing it on an actual CNC mill. Same thing for the holder. We don't care about a holder. Cutting data, we actually do care about this. Spindle speed, this is me how fast we're going to spin it. If you're using a standard Omeo X8 router, you just want to spin it as fast as you can. So it's 22,000 RPM. And the surface speed and ramp spindle speed will all adjust. Cutting feed rate. So this is whatever you have determined is best for what you're trying to do. I would say a comfortable default is 60 inches per minute. I've gone much faster, but that takes a lot of intent and understanding and effort. So 60 is a good starting point. Feed for tooth will automatically updated. The lead-in tool feed rate and lead-out will update. Transition will update as well. Now ramping, this is depending on just how comfortable you are with the concept of the ramp. I like to ramp a little bit faster because I'm watching my tool a little bit more actively. If you don't know what it is, the ramp is when your tool is moving in a diagonal in the z-axis to sort of dive into the material. It'll like go around the tool path in the X and Y while also moving down in Z. The smaller this number is, the safer it is, but it's also the slower that your operation is going to be. So it's a trade-off between end mill safety and speed of the actual operation. I like to run this a little faster. 25 is a safe enough number. 30, 35 for a 4 millimeter end mill depends on what material you're doing, but let's not get into the weeds too quickly with that. Plunge is when you plunge directly straight down. Same thing. 25 is fine. And then plunge feed, that all automatically calculates. Don't worry about step down or step over. We'll take care of that if we need it in the cam itself. And then post processor is if you're using this on like a CNC mill, you need to say what tool number it is, what tool length offset it is, what tool diameter offset. We're using this on a router, so we don't even have a turret. So I wouldn't worry about that too much. And with all that, you can say accept. And we've created the tool. It exists here back in our library, so we can say select, and boom. So this auto generates all the information from the tool. If we go to the next tab, the geometry, you'll notice these yellow lines. Ignore these for now. I'll get to that in the next tab. But my stuff is already set up the way I like it, so it actually already has a lot of the tool paths set up. Yours may not. But we'll do that here in the geometry section. So if you go over to the selection mode, there's two options. There's selected faces or diameter range. So selected faces, that lets you just click on a hole and it'll add it to the system. Now that is a valid way of doing it. And if there's specific holes and not all of them that you want to machine out, that works great. If you want to just do generally all holes or all holes within a specific range, I would recommend diameter range. You can say only machine holes, and then machine anything within a diameter of some minimum and some maximum. So I usually do 0.159, which is the diameter I use for 1032 tapped holes, to 0.3 is just sort of like the largest I would actually care about boring. I wouldn't bore larger than 0.3. You could, but don't care to. So with this, it sort of just automatically selects everything in that range. As you can see, we have a variety of hole sizes. Like this is a quarter, this is a 0.257 inch hole. These are all 1032 clearance holes. So it selects everything for me. That's really nice. Don't care about anything here in the rest. We'll go into the next tab. It's the heights tab. Yours may not be set up automatically. Mine is set up automatically. I would recommend exploring different options to see what works for you. If you don't want to do that, which I understand, exploring options takes a lot of time, just copy my numbers. So the clearance height is going to be the very top height. It's that little red plane. You want that for you to be from the, where is it? Yeah, highest of selected. And you want, I like for that about 1 inch. And I want it from the stock top. The retract height is highest from the selected, and that's from the stock top at 3/4. So you have 1 inch, 3/4. The top height, I'm gonna make sure that I want to have this one from stock top, and nothing else. So if you notice the checkbox, most of them are just stock top, except for bottom. Bottom will be stock bottom. Retract height has all three. That's just a default. I never care to change it, but I do care about the other ones. I care about clearance height being stock top. I care about top height being stock top. I care about bottom height being stock bottom. The top is how far off of the top of the material is your quote-unquote top, and that's 0 inches. So we're not, the top of our material is the top of our material. It's not 1 inch off. It's not 2 inches off. It's not half an inch under. It's exactly it. So leave that at 0. And then bottom height, it basically says, it's this one that says bottom right here. It's how far beneath the material do we want to keep the tool path running. I usually run it about 20 thousandths below, so minus 0.02. You can do more or less and experiment with that based on what your machine's capabilities are. Obviously less is a little nicer, but it doesn't hurt. That's why we have the spoil board there with the MDF. So make sure you get these set up correctly. In passes, the tolerance is currently at 0.4 of a thousandth. I think that's fine. This will be either in ramp angle or pitch. You can do a 16th pitch. You can do 6-degree ramp angle. I know those are mathematically, realistically different numbers. I have not figured out which I like better yet. I just do like a 16th of an inch, 0.065 pitch. It doesn't really matter a whole lot. If you really want to be careful on preserving your tool, you can make this 1/32. All it's going to do is just have more cycles for the bore, and who has the time for that? So I like 1/16. Comp is all in computer. All of this we can ignore. We don't care about passes for a bore. We're just making a hole. And then linking, I just leave all this exactly whatever the default is. So we say okay, and that's our very first operation. So if you look, the green is like the sort of trying to show what our stock is, and right now our stock is just we drilled out the holes, or sorry, we machined out the holes. So we'll click off that. There's our boring operation right there. So the next operation is going to be an adaptive clear. So we go back to the 2D. 2D adaptive clearing is right there at the top. So it already has pre-selected our previous tool. That's nice. We go over to the geometry section, and this is where we're going to select just these contours for the numbers, or what I say numbers because these are numbers in this example, but whatever your pocket is. So I'm just going to select these. It could be a bearing cutout. It could be anything that's not a hole. Anything that goes through the part, not a hole. It doesn't even need to go through a part, actually. Just make sure that your operation thickness is uniform. So we have we have 8 closed chains. We don't need to worry about rest machining or stock contours or tool orientation. That should all be taken care of. The heights, similar to the boring. I just double check because these don't always carry over between operations. Clearance height about 1 inch. Retract height is at 3/4 of an inch. The top height is at 0 inches, and the bottom is negative 0.02. It's all from either stock top or stock bottom. The number of passes. So this is going to be, or not quite the number, but it's going to be the information on the passes. Tolerance is, this is about 0.004 of an inch. That's fine by me. Optimal load is how much of the end mill you're engaging. I like to do like 0.375 times the end mill diameter. Can you do more? Absolutely. In fact, you can do a lot more. However, this is a number I picked back in 2018 and it works. And I haven't really cared to change that. So 0.375 times 4 millimeters. You can do math in here. And make some number. It'll figure it out. I select both ways. This isn't always selected by default, but I like to select it. Optimal load the other way will always be some amount smaller. It has some internal calculation to figure out what that should be, and you can manually change it, or you can just say, sounds good to me. So I say, sounds good to me. Other way feed rate, you can see it's like, our manual cutting feed rate is 60 inches. This thing's 54 is going to be better for the opposite direction. That's fine. Use slot clearing. I would only do this if what you're machining is a long slot. experiment it with it, doing different parts in CAM and see how it turns out. It's a fun thing to play around with. Direction should be climb cutting. And now, stock to leave. Sorry, very important, stock to leave. So we want this enabled because we want to actually leave a little bit of material around the edges. I like to leave around 10,000ths of an inch, so 0.01 inches radially. Radial is along the walls. Axial is like up down. So we don't care about up down. We're cutting all the way through the part anyways. But radial, we want to leave a little bit of material on the wall so we can come back in with that first 2D contour and clean up the edges, make them all nice. And then smoothing, you can do smoothing. You don't have to. It basically just decreases tolerance a little bit, and it makes the machine file smaller. We don't really care about file size because we're running these off of laptops that have a lot of RAM, so we're fine. This is an operation that's really helpful for CNCs that have a very small amount of storage. We don't care about multi-axis. This is a 3-axis machine. Linking. So linking sort of describes how we're moving between components and how we enter and exit different operation cuts. I would leave everything at the top the same. Allow rapid retract, absolutely. I'd leave all this as, you can either copy whatever number I have or just don't care if it's close enough. Lead-ins and transitions. That should be fine. It's going to do a ramp. It's going to do a helix ramp, and if it doesn't, you should make sure it does a helix ramp. I like a ramping angle of 6 degrees because my friend Anand in 2018 said that he used a ramping angle of 5 degrees, and I wanted mine to be more. And so that's why I use it, and it works great. So you can do that. You can be bold and do 7 degrees, but I wouldn't do it. That's because I haven't done it yet. But try it out. I don't know. Ramp taper angle. I feel like that should be a 0. Oh, I see what that is. This doesn't matter. This is just saying if you want the helix to have a taper to it. You can. It doesn't matter a whole lot. Ramp clearance height is how far off of the part do you want to start actually doing the ramp for your little helix. I have it set as 0.1 inches. Sure, that sounds great. I don't know if that's the default number or what. And then this is actually kind of important. It's helical ramp diameter. So this will say how large of a helix your diametrically your ramp should be, and then minimum ramp diameter is also very important. So this says what's my ideal ramp diameter. So if I have a big pocket, how big should that be? This is I want to say somewhat automatically generated figure, and if it's not, they've automatically generated one for me. Just make sure this is not huge. If it's a huge number, then you're left with a little puck in the middle. It's not very pretty. I'd say define huge is like larger than twice your end mill radius or twice your end mill diameter. So if I have a 4 millimeter end mill, anything larger than 8 millimeters, and I'm leaving a little piece of material in the middle, I think this is a fine number. Minimum is very important. It's something you'll play around with. The reason it's important is if you look at these slots, these may not be the largest areas we're putting our end mill in. And let's say, for example, the largest part of a cutout is smaller than the minimal ramp diameter. It just won't machine that component, or it won't machine that area. So we'll see how this plays out. We may need to adjust this number for this cam. I haven't actually tested this, but it's a very easy thing to do. But if for some reason you have like an adaptive clear and part of it isn't getting cut out, this will be one of the first things I check is your minimum ramp diameter too big? It's some random number right now. I have no idea how this was generated. I'll just roll with it, just YOLO. So I'll say okay. Now, adaptive clears do take some fair bit of time to generate. Mine generated really quickly because it's not that complicated, but give your computer time. And you can see these are actually quite nice. So you can see the red for the helix. Now, you see a lot of back and forth going on there, and that's just the trachoidal cuts of the adaptive clear. What I'm actually going to do is, and I'm going to do this for my own sake as well as this is a training, and I may as well train. This looks like something that may be just ripe and ready for those slot clearings. So I'm going to enable that. I'm going to see what the difference is. Slot clearing width, I don't know, sure. Does it change anything? No, doesn't change anything at all. I thought maybe it would be really cool if it did that. Actually, you know what? I think I can do that. I'm gonna take an extra couple seconds. I think I understand what's going on here. Let's say I want my slot to be 4.25 millimeters. Oh, no. What I want to see happen, and what I'm trying to do with playing around with this, okay, I won't do it, fine. I want to see if I can get this tool to like travel in a path, but it's a little annoying. It's cleaner when you have like a linear slot, but with all these extra things, we'll have a bunch of back and forth tracheoidal cuts, and that's fine. A little slower that way, but ultimately the reason we do this is because it's better for the tool. So that's our second operation. Sorry, I took a lot of time into that. Don't worry, it's downhill from here. In terms of time, at least. It's uphill in terms of fun, because we love CAM. So our third operation will be a 2D contour. The tool already pre-generates. If you ever want to change it, that involves a manual tool change. Just be aware of that. Geometry tab. Something of note is you're going to want to make sure that it's selecting the right side of the contour. So if you see I highlight this line, I always select the top contour. So it'll be a top and a bottom. I like to select the top. It shouldn't matter a whole lot, but it just helps with mistake prevention. So if you look, there's this little red arrow in here, and most of the time it auto pre-generates correctly. Sometimes it goes the wrong way. So if I select this arrow and see how it's now on the outside, this is saying what side of the line should the end mill be. If it's on the outside of the line, well, that's not good, because we want to cut the inside. So you'll want to click on that just to make sure it's correct. Most of the time, I think it's going to just be on the inside. Yep, that looks right. That looks right. Sometimes the software is just wrong and it machines the wrong side. It does everything you tell it to. It's just you need to make sure you're doing it right. So I'm going to select those contours, same as I did previously. 1351, 1351, perfect. And what we're going to do with this is we're going to go, heights tab is the exact same, everything should be good. There's a new one in here called the feed height. I'm going to move this up so you can see. Feed height's right here. I feed about a 1/4 inch above the stock top. Do what works for you. Feed height is where it starts the tool path from. Now here is where here's why we're here, is the passes. So what we're going to do is we basically, if you consider what we've done so far, we've drilled out the holes, or we've machined out the holes. I gotta stop saying that. We've machined out pockets, but those pockets have jagged edges. So we just want to come in and clean up those edges. So most of the material in these numbers is already removed at this point in the CAM. So we're machining, most of the material is already removed. So it's actually pretty safe for us to just dunk our end mill all the way through and then just cut along the perimeter, which is what we're about to do. So when we're doing that, I don't need to worry about how deep we are with the end mill. I'm just going to say go full depth, which is the same we do with the adaptive clear. Well, we always do adaptive clears, or almost always at full depth. Contours, I tend to do at multiple depths, where you do like 40 thousandths to 60 thousandths at a time. But for this, we're just going to go all the way through. We're going to start with this multiple finishing passes, but we're going to enable it. I want 2 finishing passes of 5 thou each. 5 thou plus 5 thou is 10 thou. And if you remember, we did that stock to leave of 10 thousandths of an inch. So that's going to help make things a little cleaner, a little more accurate. Let's look at these real quick. I think this is actually pretty fine. I think most of these are all normal. No roughing passes, no multiple depths. We'll have multiple depths in the next one. No stock to leave, no smoothing, no feed optimization. You can play around with smoothing and feed optimization. I don't think it matters a whole lot here. Multi-axis, 3-axis, don't care. Linking, so this is actually something I like to be a little particular about. In this situation, we will allow what's called lead in and lead out. Lead in and lead out is this little arc curve to get the end mill into the material. So the end mill will like swoop in and start machining. And this is fine here because we're coming in from the inside of already machined away material. I've had bad experiences with lead ins and lead outs when I'm cutting out parts, because it'll like lead in here, and while it's coming in, it'll like cut into this other plate unknowingly. So I just like to ramp those, but because we're doing a contour, finishing up, cleaning an adaptive clear, I will allow that. whatever the defaults are tend to be pretty good. And lead out exit, same as lead in. You see you have this option as a ramp. So when we get to the next one, we'll do that. And I don't care about positions, so I'll say yep. Give it a second. All right. So you can see this little green swoop in right here. That's the lead in and the lead out. So it's going to go in. You can see it's going to go in a couple times. 2 paths of 5 thousandths each. It's just going to clean up those edges, make this nice and smooth. So far we've machined out the holes. We've got a rough machining of the adaptive clear of the pockets, and we've come back in. We've cleaned up the pockets. And that's all of our, that's the whole part. That's all 6 of these parts are completely done. The only thing we need to do is actually cut them out. And that's going to be our last machining operation. So we'll do a second 2D contour. And this one's going to be very similar, but also very different from the previous one, so pay attention. We'll get through it quickly. We'll go to the geometry, and now we're going to select the parts. Make sure the red arrow's on the outside, just like the outside contour. Bada bing, bada boom. So we've selected that. Before we go into the next part, though, we're going to do what's called adding tabs. So tabs are little pieces that stick out of the part. They connect the part to the greater material stock, to the greater like the large sheet that we're cutting it out of, just so that when we finish cutting it out, it doesn't go flying away. So we'll select tabs. I like these to be about a 1/16 060 wide. You can make them a little. I would experiment with the width and the height. So you can do like I have 06. That's same thing as 0625 roughly, which is a 1/16. Tab height. The default's always really small. It's like 40 thousandths or 39 thousandths. Again, experiment. The wider and the taller the tab are, the more of a pain it's going to be to remove. Or rather to cut out, because you cut them out with shears. However, if they're too small, you may find a situation where it doesn't really hold on that well. So I would recommend something like 50, something like that. You can see these little things hold on a little bit nicer. I don't know why it's... Oh, I see what... Oh, you know what? Yeah, the tab is including the 20 thou to the bottom. Which actually makes a lot of sense now that I think about it, because we added extra 20 thou to the bottom, and that could explain why a bunch of my tabs keep breaking. So I'm going to do, if I really want 050 plus 0.020, so now that's 50 thou. Cool, I just solved a problem while doing a training video. You'll love to see it. So we have these scattered all around. I have them positioned by just even number of tabs, evenly distributed. I like 5 tabs. What I really care about is these situations right here where you have tabs next to each other, because when I'm machining out one line, the end mill will go up and over the material to create the tab. However, it's not aware of the tab on the other part. So if this is a 1/4 inch diameter, my end mill is like this big, and it's barreling down, and suddenly I shear off this other tab. So not great, but that's why you have multiple tabs. And it looks like we have sufficient number. I like to just check, see where the tabs are, and make sure that they're not going to machine all the tabs off by accident. So I find 5 is a pretty good number for that. You can experiment with that yourself. I don't need to enable anything there. Heights is the default for everything for the contours. You can pause the video and look at this if you want to copy it over. Passes, so this is pretty important here. Multiple finishing passes, up to you whether you want the outside of the parts to be super clean, and this is actually a reflection of how well do you rely on the tabs to hold everything in. I don't always have finishing passes on the outside just because that's not always dimension critical. Discuss with your design team whether the outside of a specific part is super dimension critical or if it needs to be smooth. If you would like to, you can add a finishing pass of like 5 thou. Obviously more finishing, more better, but you start reaching diminishing returns pretty quickly. And then we don't want both ways. We do want multiple depths. So we don't want to do the full cut at a time, especially if we're doing thicker material like 3/16 or 1/4 inch. I like to have like a maximum step down of like a 1/16 of an inch. If you want to be really safe, do like 40 thou. At the end of the day, you know, especially for a smaller batch of parts like this, if I add an extra pass because I have a smaller roughing pass height for all these parts, maybe I'm adding a couple more minutes to my machine time, but a couple more minutes is so much worth, it's so worth not breaking the end mill. But ultimately, making sure the end mill is taken care of is up to your machinist, so make sure that they know what to do. No finishing step downs. We don't really care about stepping down when we're cutting all the way through the part. We want to enable finish only at final depth. Rough final, use even step downs. This all looks good to me. Order by islands is very nice, so I recommend enabling it if it's not already. And that all looks pretty good. No stock to leave, no smoothing. Multi-axis is 3-axis. And then linking, the final thing is I like to disable lead in and enable ramp, 6-degree ramp. And then never 7 degrees. 7 degrees too much, if anyone asks. Even 6.5 is questionable. 6 is just perfect. Or, do what you want. I'm not the police. So we'll say okay on that. You can see where our tabs sort of end up. And this cuts that out. Nice. So if we look, we have our 4 operations, and these 4 will be used for pretty much every router job and some mill jobs you'll ever need to do, with the exception being if you don't have anything to adaptively clear, then this and this operation, the adaptive and the first contour, just may be absent. I've had jobs where it's a bunch of robot parts, but there's no pocketing, so it's just bore and contour. Very easy. So if we select our setup, not that one, select this setup, and we right click, we want to simulate. So click on this little simulate right here. This is going to show us an approximation of what our machine is going to do, and we want to make sure it's doing what we expect. So I'm going to, this down here is the speed and the forward or backwards direction. I'm going to slow it down to start with. So you can see our end mill goes in and it's boring those holes, and I can move around. I can zoom in. See how it's doing little spirals? So I know that that's going to be pretty safe. I'll take this, I'll move it up a tiny bit. Be careful, it increases the speed seemingly exponentially. So when you move it up, it goes a lot faster. So you don't want to, you'll find a point where you like move it up and then the whole part's done. It'll just go through like 10 operations at once. So see, I'm barely even moving it. So it does all the boards. I'm going to slow it down a little bit. All right. So it's going in. Okay. I don't know why I didn't finish the 3. This may be a situation where you want to enable order by the islands if that's not already enabled. In fact, I'll stop this and I'll go check that real quick. Is that an option, or is it just the stay down that it doesn't like? Oh, it's not letting me do order by option by islands. Shame. Oh well. Yeah, it's fine. There's some setting you can do to make it not go back and forth, but for this it's fine. Let me speed this up a little. Cool, and that's going in doing that contour, so it's doing that 2D contour 1, it's going back to and sort of contouring out each one. And now it's cutting out the components. You can see right here, this is what I was talking about, what I was worried about. I'm gonna pause this real quick. With the tabs, let's see. So this cutting line cut this tab, so this tab's not actually holding on to anything. Same with this tab, right? So there's nothing actually holding on to them here. But this tab's holding on, right? You can see it's holding on to the main outside material. The rest of them are. So we just want to make sure there's sufficient tabs holding everything together. And cool, that's the entire thing. So this is what our stock would look like afterwards. We have a whole bunch of little holes. We have some pockets made, and we have our parts cut out. So that looks great. That does exactly what I wanted it to do. Maybe not exactly the way I wanted it to do it, but the end result is precisely what I want. So that's great. So we can exit our simulation. Give it a second to reload. Make sure at this point you save if you haven't already. Generally good practice to save throughout the process. So I'm just going to call this CAM training. Over here off to the side. That's your CAM assembly. And from here, once you're done, you're just about ready. You can right click and say post process. Now you're going to want to select a post that post sort of defines how to translate the CAM we just did into the specific machine that we're going to be machining it on. So we're going to choose from the library. Unless you have a very specific CNC you're intending to use, I would recommend just a generic Mach 3 mill. So if I go down to ArtSoft, Mach 3 mill, that's going to be great for something like an Omeo CNC or a Velux router or something simple and not too industrial. So yep, Mach 3 CNC, Mach 3 mill. I'm going to select it. It'll want to put it in some location. You're like, oh, I want to find where you should put where should I put the posts that I'm using? So I just put them over in local and say select folder, copy to my posts. Yep. So you have Mach 3 mill enabled. Program name and number / file name is precisely what it says. If I save this as is, it'll be saved as under the name of 1001. The reason they do this is some industrial CNCs only accept file names that are a string of numbers. But Mach 3 doesn't care. So I would do something like whatever your naming convention is. So I'm going to call it CAM Training 01. That's to be the name of it. So your output folder is wherever you'd like. You can select this and output to the desktop. It's going to default to some NC programs folder, some folder within a folder within a folder within a folder. I recommend selecting a new folder and doing that. NC extension is the document extension. .tap is a great one, so just use that. I wouldn't worry a whole lot about what's going on over here just yet. That's for a little bit more custom stuff. And then you say post. You'll get a little NC code posted successfully, and you're done. And that's it. You'll be able to take that if you save it to the desktop or if you wherever you put it. Put that onto a flash drive, or you can put it in a Google Drive. Wherever you do, whatever you do to get the machine that's running the router to get the file, do some sort of file transfer there. And then you can open up the .tap file for your router, and you'll be done. You'll be able to run it. So that's CAM in a little under an hour. Good. I was getting worried that this would be a long and boring video. But yeah, this should cover pretty much everything you need to know for whatever kind of parts you need to make. So I hope you found this helpful. And if you have any questions, always feel free to reach out to me. Until then, have a good one. Bye.